So we're just starting. Hello, thank you for coming to the second day of our conference. And we're starting with the session on quantitative and qualitative approaches in research evaluation and the COARA agreement. In our first session, we have the great pleasure to have from California, John Ioannidis, who will speak about in defense of more and better quantitative assessments. The floor is yours, John.
Thank you, Zaharia. Good morning, everyone, and good evening from California. Let me see if I can share my screen. Okay. Is it visible now?
Yes.
All right. So some disclosures. I think that I have no conflicts of interest other than trying to be a scientist, which means that I'm probably unavoidably very biased. Much of my work is studying bias, so I may be even more biased, so don't take very seriously everything that I say, at least without some healthy skepticism. Some preemptive comments. Quantitative assessments are very widely used for a long time, for single scientists, for teams, for institutions, and for countries. Many of these assessments clearly are misleading, using metrics that are flawed conceptually, inaccurate and or biased in measurement capacity, and highly gameable. Calls to dismantle some of the most flawed and gameable metrics, for example, impact factor, have not been very successful. Nevertheless, an overreaction has been to dismantle all quantitative assessments and replace them with qualitative in-depth evaluations by topical experts, peers, or other stakeholders, which could include also patients, community, and many, many other stakeholders, depending on the circumstances. My main theme in this presentation will be that dismissing quantitative metrics would be the worst possible outcome of reward research reform, even though we need a balanced and careful use of different approaches. I think that dismissing them, which I think is something that I see happening to a large extent, will be a very big mistake. Here's one example of how difficult it is to measure what we want to measure or to capture what we want to capture, either quantitatively or qualitatively. For example, we want to reward innovation. No one would doubt that this is a worthwhile goal, but can we even tell what innovation is? There's hardly any reliable method to predict innovation ahead of time. The vast majority of honest and excellent scientists probably never produce anything that is highly innovative, despite continuous hard work and every good intention. And in fact, innovation takes many years, often decades, to materialize and translate itself. So even if we could measure something, it would take probably 30, 40, sometimes more than 40 years to be able to tell that that was indeed so. There's many assessments actually that suggest that even when you ask scientists about their highest impact work that has received the highest citations, and you ask them what was really important about that work, what do they think that work did, it is not innovation and disruption that they claim to be the key feature. It's continuous progress, it's broader interest, it's greater synthesis. It's an addition of incremental steps most of the time rather than disruption and surprise. And in fact, if you try to capture answers that deal with revolution and disruption and others that deal with kind of stepwise evolution, it's not that one is against the other. They may coexist. If you see red links between these different aspects, that means that there's a positive correlation. If there were a blue link, that would be a negative correlation. There's really no negative correlation in that survey. Much of the argument that I will present, you can find in more detail in a paper that I wrote in PLOS Biology with Zacharias in defense of quantitative metrics in research assessments. And our starting point is that science is very complex and nuanced. Measurements also need to be complex and nuanced accordingly, with proper centralization and standardization, with acknowledgement of limitations, with complementarity, and with metrics that probe for gaming of other metrics. I think that last part is very important, and I will spend quite some time on that. This is one aspect of how complex science is, and to measure complexity, we need quantitative methods. This is one effort, along with my colleague Kevin Boyack, to create a map of science. This is just 20 million papers. We have about 200 million papers currently. So 20 million papers, 2 million patents, creating 200,000 clusters, 200,000 sub-disciplines. And I'm showing you with an arrow my best paper, which is a speck of dust and a speck of dust and a speck of dust somewhere around here. So if we want to have research assessments, we need to be able to place a piece of work against that very, very complex background of very different disciplines with very different practices. This is another map that shows 500,000 scientific subdisciplines. There's very different features in these subdisciplines. For example, there's different levels of industry involvement, which might translate to applied or market-oriented research. The deep colors here are proportional to industry authorship in papers that are published in different fields. There's different levels of commercial interest reflected in patents, which again, in many research areas, that would not even be something that one might think about to capture, a lot of very theoretical disciplines, while in others, it may be very important, and one would like to have quantitative assessment of how much of that was translated to something that could be patented. There's wide variability on whether we have, for the life sciences, clinical applications. So in the whole spectrum, from basic discovery to translational research, clinical research, evidence-based implementation research, you would need different metrics to try to capture what exactly has been achieved in each one of these fields. However, despite that heterogeneity, I would argue that there are some desirable features for all quantitative metrics that they would be good to have no matter what. One is that I think we should have metrics that are public good with low marginal cost. There are some metrics that may be very expensive to generate. And I think that if we think that they're very important, then we have to come up with ideas on how to make their production and their updating more of a public good with low or ideally even no cost. Then I'm in favor of science-wide global coverage because that allows for some comparative assessment of one field versus others and having one field learn from what is happening in other fields. They should be transparent and reproducible, not black boxes that no one can really tell how they were generated and why is that number emerging. Centralized is a major problem in most quantitative assessments that depend on having each candidate, each institution, each organization generate their own metrics, even though often some guidance is given. There's so many degrees of freedom and so many analytical choices that they can get very different metrics for their own selves and their own institutions. Standardized with proper adjustments, for example, adjusting for the scientific fields and subfields and connectivity of the field, done in a uniform way rather than being reinvented on each occasion. I think it's very easy to play with standardizations and adjustments so that people will get the best looking metrics for themselves, but that's not going to be very reliable. Reduce gaming potential. And I recognize here that practically every metric can be gamed, but some are more difficult to game compared to others. And I think this is very obvious once you start comparing different metrics. Recognizable gaming. Recognizing that some gaming might be unavoidable, are there other metrics that we can develop that can give us some insights about the gaming that has happened and the processes that have been used in the gaming? For example, excessive self-citations, hyperprolific excessive publishing behavior, citation orchestration, and so forth. And I'll show you some examples in that regard. We need metrics that capture best research practices. So moving beyond productivity and impact, we can look at the machinery of how research has been produced. Things like data sharing, code sharing, protocol registration, and others. And finally, also indicators of poor research practices like retractions, signs of image manipulations, paper mills, editorial nepotism practices, and others. Many of these diverse metrics we can measure with most, if not all, of these premises in place. For example, we have relatively straightforward ways that we can capture across the entire scientific literature if we have access to an XML version or a PDF version of the papers, of millions of papers. We can readily capture which papers are sharing raw data with pretty good validated sensitivity and specificity. This is one such exercise that we did across the entire PubMed Central Open Access corpus over 30 years. You see how it looked like when you compare proportion of sharing data in publications from different countries. Until very recently, very little was being shared, so there's lots of darkness around the globe, but the situation is getting much better. We can do the same for registered protocols, which is another feature of good research practices. And again, this is from the same assessment of PubMed Central Open Access. Scientists will respond to what gets incentivized, and they're attracted by what is hot, by what gets incentivized. COVID-19 pandemic was a classic example. We saw that in 2020 and 2021, 98 of the 100 most cited papers published in 2020 and to 2021 were related to COVID-19. Practically every single scientific subfield, if you divide science into 174 fields, according to the Science Metrics classification, had some experts who moved into performing COVID-19 research. Of course, it was a major problem and everybody wanted to save lives and improve the situation, but there was a very hot and very desirable incentive structure. We had 720,000 scientists working on COVID-19 within about a year and a half from the onset of the pandemic. And when we repeated that assessment recently, we saw more than 2 million scientists with Scopus author ideas having published at least one COVID-19 paper. So incentives can make a big difference in moving the scientific workforce towards productivity or generation of some evidence that is thought to be desirable, important, relevant, hot, rewarded. Reproducibility factors are important to improve. So we can use metrics in a way that may foster more reproducible science, meaning metrics can capture practices that we think, and we have some evidence, hopefully more solid in many cases, not on every single aspect, but in many of these, that if they're more widely adopted, we will get more likely to see results that are true, that are reproducible, that are replicable. So we can capture with quantitative metrics teamwork, large-scale collaboration, performance of replication, registration practices that I just showed you an example, sharing, again, reproducibility checks, aspects of conflicts for sponsors and authors, use of statistical methods or misuse of statistical methods, use of some standardized approaches to doing research, design standards, risk of bias assessments, and many other aspects that relate to improving the chances of getting reliable research. This is the data that I showed you, the maps earlier of the globe of the entire PubMed Central Open Access. We have for every single paper in that corpus an assessment of data sharing, of code sharing, of protocol registration, of claims of novelty, of mentions of replications, of mention of conflicts of interest, and of mentions of funding. So in principle, you can generate metrics for every single scientist and for every single institution that includes scientists who publish these papers very readily in a centralized and a standardized way. This is another snapshot looking at how frequent are these research practices? They're becoming more common, but not as common probably as one would wish in terms of sharing, for example, data and code and registering protocols. We can see the evolution of these practices across these subdisciplines of science. This is mapping, sharing of code and data and disclosures and protocol registration across all these subfields of science. So you can see that some fields are doing better than others. If you want to perform research assessments within a field, you have to calibrate for what is the performance within the field compared to other scientists working in the same vicinity. And you can do the same for journals. If you want to assess journals, you can map the performance of journals across all of these metrics. For example, in the top left panel, you have the proportion of papers that share their raw data. And there are some journals that share raw data on more than 70% of the papers that they publish. And of course, there's many, the large majority that share the raw data on nothing that they publish. So you can have comparative assessments of journals, publishers, groups of journals against each other. Over many years, we have been generating a standardized citations metrics author database that is annotated for scientific field and subfield, along with my colleagues from Elsevier, Scopus, and SciTech. We make it publicly available. It includes about 250,000 scientists with very detailed data. Instead of just giving, for example, just number of citations, we give more than 25 pieces of information on each one of them. And you can have also percentiles that you can rank all the remaining authors. So we give the top cited, which is about close to 250,000 currently, but someone can place practically any author ID against these percentiles, for example, for a composite citation indicator that takes into account citations and Hirsch index and Schneider co-authorship HM index and citations to single author papers and first author papers and last senior author papers and so forth. One can also look at biases in some of our assessment practices. For example, one can look at gender imbalances. And this is one such assessment that we did with the same database with the ability to look at close to 5.8 million authors who have published at least 5 papers indexed in Scopus. We could assign gender with very high certainty for 5.8 million. In some, we could not, because assignment software has an uncertainty that is substantial in several names. We could see the evolution of gender imbalances, how they get healed over time across different disciplines. Again, this is dividing science with science metrics classification into 174 fields. And you see in cohorts of scientists who start publishing in different times, in different eras, the senior cohort who started before 1992, then you have those who started in 1992 to 2001, those who started 2002 to 2011, and those who started after 2011. You have a larger proportion of women in the top cited ranks when you look at career-long citations and single most recent year citations. One can look at the evolution over time in each of these disciplines, so calibrate each discipline and get a sense of the imbalances. One can also do separate analysis according to country or groups of countries. For example, this is grouping according to high-income and non-high-income countries. I think priorities may be different in different countries. Maybe the goals that one wants to reach with research assessments and with incentivizing different aspects of productivity or impact in the workforce may have a different flavor in countries that may be lagging behind in terms of some of these biases. One can also look at career trajectories. For example, in that same analysis, we could compare men and women in the youngest cohort, those who started publishing in 2012 or more recently. We could get a random sample and see what do these people do. These are scientists who have less than 10 years of a publication record. And what we could see is that still academia seems to be the dominant occupation for these people. Only 4 of them out of close to 200 had reached the rank of full professor. And in fact, all 4 of them could be spurious, and that maybe their age was not as young as we thought, because these were all cases from countries where it's possible that they could have started publishing much earlier than what is documented in Scopus. So one can see that in the current reward system, young people, unfortunately, do not get recognized very promptly, and it takes a very long time for them to get tenure, which I think is very unfortunate. Some people have published data showing that research is becoming less disruptive over time, and perhaps the very prolonged maturation that we have for our scientific training is responsible for that. This is another paper that I published with Zacharias, which is also very relevant to our discussion. We argue that one can use metrics against gamed metrics. And here's different types of gaming behavior that one should take into account. I would classify it in 5 different categories: authorship-based, citation-based, editorial-based, journal-based, and outright fabrication. Outright fabrication is paper mills, spurious content papers, spurious massive publications for studies with demanding designs that it's improbable that they're real. We can measure quantitatively that a team suddenly accelerates productivity 6,000 times. That's not very likely, especially if it comes from a location that has very limited resources and are not even able to recruit, for example, the patients that are claimed to be in the research designs that are being published. But beyond fabrication, we have other things that are not fraud necessarily, but they're clearly gaming the system. Authorship-based gaming includes, for example, massive authorship without necessarily having the real contributions to deserve authorship, gift authorship, honorary authorship, and so forth. Or it could be teamwork with over-attribution of authorship, with too many people. The same paper that would have had 3 authors in one environment may have 300 authors in another microenvironment. We can capture all of that with quantitative metrics. We can give a very good sense that there's orchestration of authorship. Citation-based gaming includes massive self-citations, citation farms, H-index gaming has been described. All of these can be measured quantitatively, pretty rigorously. Editorial-based includes editorial nepotism. Again, there's studies by Floriano Dead, Dorothy Bishop, and Yana Christea that have looked at editorial nepotism across the literature. This is something that quantitatively can be captured. Journal-based, you're all familiar with journal impact factor gaming. And it's so unfortunate that this metric has been entrenched and we cannot get rid of it, because it's probably lost its ability to tell us anything other than maybe a little bit of journal level information, but even that is problematic. And here's a few examples to show you how quantitative metrics can help us detect gaming. Implausible increase in productivity. These are examples of situations where you have an author who's publishing very few papers in their late 30s and early 40s, and then they get a director's position or chair position, and suddenly they accelerate their productivity about 10 or 30-fold. And they reach levels that are completely difficult to imagine. This is data including only full papers. I'm excluding here editorials and letters and perspectives and narrative reviews. These are full papers, and some of these people reach levels of 100+ full papers in a single year in the productivity boost that they get. Several years ago, we looked at the entire scientific literature to look at scientists who publish a paper every 5 days. which means more than 72 papers, full papers again, excluding all the papers that can be drafted pretty quickly. I mean, an editorial, of course, someone could publish many, many editorials. There's many editors of journals that publish hundreds of editorial and column type of articles every year, but a full paper would be pretty tough. And at that time, we had seen that there is some plateauing effect, probably after 2012, was no longer any increase in the number of such hyperprolific authors. Nevertheless, we repeated that exercise. Oh, and let me show you also, we sent a questionnaire to these authors to try to see whether they fulfill Vancouver criteria, and they admitted that in several circumstances they did not. So we repeated that exercise recently, and we published that paper a couple of months ago, looking at data up to very, very recently for extreme publishing behavior. And we see that even though back in 2016, there was some suggestion of some plateauing, that is not the case. Actually, we have seen a very rapid increase over the last 8 years, or up to 2022, when our data end for this analysis, especially in non-physics areas, because physics has always had a pattern of extreme publishing behavior with papers that were generated mostly at CERN with hundreds, if not thousands, of authors in each of them. But non-physics areas have now reached about the same level as physics. And these hyper-prolific authors, these authors with extreme publishing behavior, probably are a mix of some who are amazingly prolific just because they're very, very talented. I have to say I'm a maniac in writing papers, but I'm very far from reaching these thresholds. There's about 30,000 people who have published more papers than I do in single years. So I just don't know how they do it. But in principle, these authors account for a large share of the authors that occupy top ranks in terms of citation indicators based on these huge productivity that they exhibit. So one can measure that, one can track that, one can see the trajectory, see whether that looks logical, rational, plausible, or implausible. One can also look at non-research authors who are becoming very influential in high-impact journals. For example, journals like Nature, Science, or BMJ. Most scientists would see it as a milestone in their career if they publish a single paper in Nature. And many research assessments for recruitment and promotion will just ask simple questions. Have you published in Nature, Science, or Cell? And if not, don't bother to apply for a faculty position here. If you have, then that's a green light and you can move ahead. A single paper might be opening the gateway to a career. Now, there's people who publish more than 200 papers in Nature, or more than 200 papers in Science, or more than 200 papers in BMJ. In some cases, they publish more than 1,000 papers in each of these journals. And I have mapped across all science the prevalence of such authors. Some of these papers actually get very heavily cited just because they appear in these journals that they do appear. And these are papers that go through no peer review. These are papers that can be published practically overnight. They're the editor or kind of commissioned by the editor. So they can have very rapid turnaround and shape several scientific areas very quickly. I mentioned self-citations. This is another example where by looking across all science for each discipline, I'm showing you here high-level disciplines, but you can do the same for sub-disciplines and sub-sub-disciplines. You can set thresholds on what is too many self-citations. So you can say that if you work in agriculture, the 5% threshold is 27% of your citations being self-citation, and the 1% is 36%. Conversely, in physics and astronomy, it's 41% and 53%. And you can do that for any level of granularity that you want. Another piece of information that you can add is research practices and outcomes that are not desirable. So not just the positive aspects, but the negative aspects. And we have some work in the making that we will be hopefully publishing soon on linking the entire Scopus database with the retraction watch database on retractions. So we can see how many scientists have had retracted papers that are not due to publishers' errors and may have some author responsibility. And these are some data looking at the most cited scientists. About 4 to 5% of them have some retracted papers in their career. Clarivate has decided to exclude these scientists from their list of highly cited authors and scientists. I don't think that this is a good idea. We don't want to necessarily just penalize retraction, because retraction is a way to correct the literature. And in some cases, perhaps in many cases, people should be congratulated if they retract a paper that they feel was erroneous, and they just want to correct on their own initiative the scientific record. But at least making these data available allows people to have then a more in-depth look to see what these retractions are in each case, and perhaps the reasons and the settings and the circumstances would differ from one case to another. These are data for different countries. These are the countries that have the highest number of highly cited authors. And you see that some countries have higher proportion of people who had some retracted papers. For example, India is at 9%. Some countries that are not shown in this list, like Pakistan, Iran, and Saudi Arabia, have proportions of people with retracted papers that are even higher than that, in the range of 10 to 25%. Pakistan has about 1 out of 4 of their top authors having had retracted papers. Citation orchestration. This is a preprint that I've worked with Yakos Avdemon, Michalis Varzirgiannis, and their team at the École Polytechnique in Paris. We describe some metrics that can be used across the entire scientific literature to have hints of small-scale and large-scale citation orchestration. Meaning,
you still have 10 minutes.
Yes, thank you. You can see that they generate more citations perhaps than would be the normal situation. So even within small citation cartels or within large teams of scientists that cross-cite each other. Going back to the paper with Zacharias, this is a table that we provide some examples of how you could have a very heavy quantitative metrics assessment for different scientists. And we give examples for 3 scientists. And the type of information that you can get pretty readily at the moment. You can look at their main scientific subfields, the secondary scientific subfields, the ranking based on composite citation indicators in their subfields, proportion of self-citations, ranking of the proportion of self-citations in the main scientific subfield, whether they have extreme publishing behavior, whether they have papers with many, many other co-authors. So how many co-authors the scientist has published over 50 papers with, the ratio of total citations over the Hirsch index squared, any evidence for citation farms, proportion of citations to non-full papers, number of retracted papers, number of detected paper mill papers, percentage of papers published in journals that lost their impact factor, proportion of open access papers, proportion of papers with data sharing, proportion of papers with code sharing, proportion of papers with protocol registration. All of that information can be readily available, and you can get a pretty rich profile on different individuals, and of course also at higher levels of integration. Now, I didn't mention anything about qualitative metrics because I'm sure that other presenters will discuss them. And I have nothing against qualitative metrics. I love to do qualitative assessments myself, but qualitative assessments, to be done well, they need time, they need effort, they need far more than the low cost or no cost automated, centralized, standardized approaches that we can have for quantitative metrics. This is a preprint that we have released in arXiv about the cost of competition in distributing scarce research funds. Some of the qualitative assessments already are taking a large share of the very limited research funds that we have. If we want to make them even more common, it's very likely that they will absorb all of our research funds. And the only thing that we'll be doing will be just assessing each other and not doing research. And I don't want to see that happen. I'm happy to be assessed and to be found to be the worst scientist, but please let me do my research. And I think that other people will think the same. We need to find creative ways of assessing scientists. And of course, metrics are just part of that process. We need to look at multiple dimensions. If some of them can be measured with metrics, that's good. If they cannot, we should acknowledge it. Most of our faculty handbooks for recruiting and for promoting mention none of that. They just look at very old-fashioned criteria. But I'm hopeful that when I see discussions in recruitment and promotion committees, people do think and do discuss many of these aspects in one way or another. To conclude, quantitative assessments need to be improved, not discarded. Metrics to probe gaming of other metrics can be readily developed and implemented. Centralized, standardized data are a low-cost commodity that can be used widely, while qualitative assessments are possible mostly in elite, high-resource institutions and have entirely unknown sensitivity and specificity. I hear people say that, oh, you always recruit great people at Stanford. Yes, but maybe. But we leave out probably 300 times more who are at least as good or perhaps even better. Just we have lots of people who want to come here. We need more and better quantitative metrics that capture the dimensions that matter. And eventually, all metrics are surrogates. They're not the true value of research. This applies even to qualitative assessments. This means that they should be treated as such with due caution. Thank you very much.
Thank you. John, hello, John, can you hear me?
I can hear you, yes.
Very good. So let's address a few questions to John using our microphone so that he might be able to hear as well. So any questions, please? Yes.
Hi, I hope you can hear me okay. Thank you ever so much for that really interesting talk. My name is Elizabeth Gowd and I am one of the vice chairs of the Coalition on Advancing Research Assessment. I totally agree with you. There's a very important role for quantitative metrics to aid our understanding of the scholarly enterprise, to probe for gaming, as you described. I think that's really important. I think where our views diverge is probably around the use of quantitative assessments for recognising and rewarding individual researchers. And I just wondered, given that your own research has shown that men outnumber women threefold amongst the top cited authors, how helpful do you think it is to share that database of highly cited scientists, given that this is likely to embed that status quo?
Well, I'm in favor of making data sets publicly available. So I think that making data available is a good thing in principle. Now, a data set can be misused, it can be misinterpreted, it can be used for the wrong reasons. And I see that very often. But what is the antidote to that? I think it's not to hide the data, it's to make them more visible and to try to explain in each situation what they might mean, what their limitations are, and what might be better ways to use them. It's a challenge, and I don't have a perfect answer, but my feeling is that having data sets available, especially if they're centralized, standardized, and transparent about the way that they're constructed, along with the limitations that they have, is better than not having these data sets. It's a starting point. It's also a research tool.
More questions? I don't think you are.
Hello, there you go. Thank you, John. I'm Ioannidis from University of Cyprus here. Very simple question. What do you think of the big rankings like Times and QS and Shanghai and so forth? Is that a service to science?
I couldn't hear the question well. Maybe if someone could come closer to the microphone, or
the rankings that are produced by Times aggregation and Shanghai, Shanghai ranking, the QS ranking, and so forth.
So about Shanghai and US News and other rankings, I think I was one of the first to write a very damning piece in the early 2000s when they had just started being released, that these were horrible ideas. Now, I think it's more difficult to appraise large-scale agglomerates of sciences, and institutions, universities are one such, because one is aggregating and averaging across hundreds and thousands of scientists and very different aspects. And even with some stratification, it's still a high-level aggregation. So in principle, I'm not very much in favor of that level of assessments. I have an individualistic bias in assessing. I think it's difficult to appraise single science. When you start going into appraising large aggregates, which is something that many organizations want to do, I think it can be very misleading because the average effects do not represent neither the best nor the worst, perhaps not even the average median scientists in that conglomerate. And I think that some of these results may seem intuitive, like, okay, so these universities seem to be ranked very high. Yes, we agree they are great universities, and these others not. But no, that's not really very helpful. And I think it just perpetuates some very misleading thinking about what we try to do.
Other questions? John, I have a question. How do you think we should proceed? What should the next step be in order to achieve the low marginal cost available rankings? For example, according to the list that we had in our recent paper, that shows which is a detailed list that shows in fine details characteristics of the publication pattern of a given scientist. So in order for them to be centralized and publicly available and acceptable by the community, and we don't want them to be proprietary and driven by individual corporations or specific interests. In practical terms, how is this achievable? At least in terms of ideas about how to move.
I think that there's a fine balance, because obviously there's many commercial players in this game. So I'm in favor of something that would be publicly available, which also means verifiable and transparent. For many, if not most of these metrics, this can be done at the moment with different data sets. These different data sets, some of them are completely publicly open, others probably need subscription, but one can work around some of these limitations. In principle, I think we need to move towards publicly available, centralized, standardized data sets that also confer a pretty accurate sense of their limitations and their error rates. So well-characterized data sets will have validation exercises that we know that for each of these variables, there's X% of error. And also there would be a feedback mechanism that errors could be corrected over time. I don't think we will ever have the perfect data set in any sort. But we have data sets that are pretty reliable for the very vast majority of scientists. So trying to make them more available and more open would be worthwhile. And that means that the cost would be brought from low to zero. Then it's an issue of how people want to use these more granular profiles, hopefully in a creative way rather than in a gaming way.
Any final questions? All right. Thank you, John, so much for staying with us so late for you. So we'll let
Thank you very much. I look forward to listening to the other presentations, probably when I wake up, though, and I realize that they're being recorded.
Great.
Have a wonderful day.
Fantastic. Thank you so much.
Bye-bye.